This video is how quantum numbers explain electron subshells as a hemispherical coordinate system. Now, the main concept in chemistry includes understanding each of the elements, obviously their properties, and then how they come together into molecules and more complex systems. Now, this is a basic thing, so we'll introduce just the atomic model, which is 3D engineering to understand it. And to do that, you have to understand the various interactions that occur, both electrostatic and nucleostatic. Nucleostatic being what they call the strong nuclear interaction and the weak nuclear interaction. And combine those two factors become electron subshells, what I call the two-cylinder. Now, as you can see in chemistry, almost everything is interlinked. You have to build on concepts. Now, specifically, there are those two interaction types, and there is this hemispherical coordinate system that is both quantum numbers and electron subshells. Then you will learn the shell and subshell logic. Why is the periodic table in 2, 4, 8, 8? And the math of that, which is the two cylinders, satisfy the requirements of Bose, which is the proof of statistical mechanics. And it's at that level that you start to have statistical mechanics. So the important field distance, almost everything in engineering is based upon this. And I'm going to do just a distance versus strength graph here at the right. So this is the distance, and this is the strength. And 1, in this case, is the Bohr hydrogen radius. And that's for the simplest 1 electron, 1 proton system. So obviously you've isolated as best you can all of the factors to get that. Now, the first thing to understand that there are two main radial fields. The electrostatic, that's charge, and this extra 1 over r, which I relate to the strong nuclear force, hence nucleostatic. And that at that distance, they have the same strength, which is Planck's constant, the h hat times c, the speed of light version. All right, so the interesting thing is that the first is electrostatic is opposites attract. This graph is physics positive is repulsive, an acceleration to make the distances greater, positive. Physics negative is attraction, making an acceleration to reduce the distance between them. Now, according to this, electrons will fall into the nucleus, just like the famous Rayleigh Jeans versus Planck schedule. And there they had to find the secondary thing that balances that. And what I've said is that this is the extra 1 over r that Bohr figured out the correct math, but he used the wrong name. He called that angular momentum or orbitals. And I believe this is a static field, a static interaction from the strong nuclear, and it's at an extra 1 over r. So this is 1 over distance squared, and this one is 1 over distance cubed. And those forces are opposite, always. As a result, you get this black line, which is the overall net of those two. As you can see, it is positive and then it goes to 0. So there's this balancing point, and that balancing point is Planck at Bohr. And that's a new concept. Most people don't think of Planck. They think of it as a abstract concept. But this is a field strength, and it happens to be important because it's the field strength of this at Bohr and also that, which is in the opposite direction, so you get electrons doing that. The other interesting thing is this repulsion. So when this electron comes in, you basically get a wall of repulsion, a natural wall at the Bohr radius. So electrons want to fall into the nucleus by opposites attract until they get this opposite overwhelms them. So let's talk a little bit more about that Planck at Bohr equilibrium. Okay, this is the one-to-one electron, but this is physics positive. It's going through zero from a positive to a negative at greater distances. So when the distance is less, it's physics positive, pushing it right back. And if it gets smaller, if it gets larger distance, it's pulled forward because this is physics negative attractive. So this is a self-correcting equilibrium. It's a natural balancing point that electrons stay in fields. Now, the reason that nobody has discovered this or explicitly is because of this. The red line, the net 2, and the electrostatic out here at about 4 times the Bohr radius, which is about the size of every atom's field of effectiveness. These two are exactly the same. You can't see the difference. Think about it. 1 over distance cubed here, as the distance, say, gets 10 times the Bohr radius, that's 10 cubed. That's 0.001. Immaterial. Almost nobody can calculate that. Besides that, the instruments that we're using to measure it are, guess what? Electrostatic. So we use electrostatic, we find electrostatic, and then we think there's these strange things going on inside the nucleus. Well, in fact, it is. Because once you get inside the nucleus, the strength is nucleostatic. And that's at a different exponent. And also, as we'll say, with a weak field, starts to have the magnetic. So first, let's see, that's a simple one-to-one, one proton, one electron system. Let's make it the next most simple. If you add a second electron to the system, say a helium atom, what happens with that? Again, you have the net 2 force attracted up to that wall at the Bohr radius, but electrostatics are minus sign, okay? The multiplication of that is positive, like kind repel. That's the math of charge particles. So they want to be as far apart as possible. So when people talk about Pauli pairs, it's not like in a Lewis diagram where you have two here, a pair, a pair, a pair, a pair. No, that pair is all the way over on the other side. It's got to be there because this is impossible to overcome. If it comes over here, it's attracted here, but is repelled there, pushing it right back to that spot. Another one of these self-sustaining equilibriums. Pauli pairs are self-sustaining equilibriums at 100 degrees, at 80 degrees. See, this is what it looks like. You have the repulsion if it gets out of position, and you have the attraction of the nucleus. But in vector math, you basically translate this one up to here in step 3, and then you add these two dimension by dimension, and effectively you're just pushing it along this circle until the net of those two vectors is right back here at 180 degrees. Okay, so now let's go to the next most complicated. So now I've got more than 2 electrons. I've got a whole set of them. It's called an electron subshell. And that's where the magic starts to happen. The unusual, crazy things that's called statistical mechanics or quantum behavior. Okay, an electron subshell is 2 hemispheres around the nucleus. This little oval here is the nucleus, and going through it as a straight line is, it has an axis. Nobody's really talked about that before. You have an electron here, and then you have another set which is over here, but that's sort of offset by 1/2 phase. It's not up here at the top, it's down here at the bottom, so they can be aligned. Similarly, there's another one here and another one here, matching. So you get electrons at a cylinder, surface or end cap rim and an end cap rim. Now what happens is another set of equilibriums occur. You see, you have that basic one that we talked about, the proton electron electrostatic falls into the nucleus, offset at the Bohr radius by strong nuclear force. So this is the equilibrium that's basic. But now you have these other electrons, and you also have a weak force. Weak force is not radial, isotropic, a fancy word for the same in every direction. A weak nuclear force is towards the axis of the other particle, that axis being this longitudinal line, this nucleostatic axis. And that has a strength based upon the distance and the inclination angle. And you also can think of it as a longitudinal angle. Inclinations are from the poles. And since I know that's the axis, I like that wording better. Longitude is through the equator, which is what you will see on a globe. So you can think about this as a longitude on a globe and various evenly spaced latitudes around it. So that weak force, so there's the three fundamental forces: electrostatic, strong, weak. But guess what? In this multi-particle system, you have other units here. That is electrostatic like-kind repulsion. So just like we had equilibrium now in this way, we have the cylinder surface equilibrium. And so the pulling of these further, because these are electron units, they all want to pull in and they bump off each other. And now only when you have off-axis, okay, electron sets of subshells do you have statistical mechanics and thereby quantum behavior. It does not occur one-to-one. So what are the quantum numbers? Okay, I think of them in an easy way. You're taught all these abstract numbers, but really it is just a hemispherical coordinate system, okay? And you're using the hemisphere because eventually that will make the math easier. So I think of this like a globe. There are, first number is a layer, okay? You've got a, first layer, second layer, okay? The second number is the inclination angle. And again, that's the same as a longitude on a globe, but since we're using the axis, we want to do an inclination, all right? The third number is the latitude. How many count of electrons are evenly spaced at that latitude? And again, the inclination, the second number, is how many are there from the poles to the center. And then the fourth number is which hemisphere, because you still have these Pauli pairs at 180s, one in this hemisphere, and there's always, tries to always have a second one in the other hemisphere. Now, these were called quantum numbers. So this is 1, 2, 3, 4, 5, 6, 7 in layers. But the interesting thing is the second number starts at the pole. That's 0. So this is 0, 1, 2. And so then you take 0, 1, 2, and you try and space where those would be in evenly balancing. And the same around here. You have 0, and then you have plus and minus to the meridian, with remembering that the meridian in the other item starts at 180, so the plus minus is a little different. Okay, so that is the approach. So now when you look at atomic cells, you have 0, 1, 2, 3, or 0, 1, 2. And obviously the math sort of helps you to space those. But now you have engineering, so you can try and figure those out. So there's one final step to understand both quantum numbers and this periodic table of elements. You see, if you have those two hemispheres with the one down and the other side at the back, you can go to the next layer. If you line them up exactly, they're going to be the same. But if you offset them by 1/2 phase, they can fit together a little tighter, pulling it towards the Bohr radius. As a result, you will almost always find two sets that are paired, with one layer at the 0 and the second layer counting plus and minus in quantum numbers from 180. Now this picture up here at the right is an actual early picture of electron subshells. And There's the subshell, uh, it 1, but there's 2 and 3, sort of close to each other, interlaced. There's 4 and 5, interlaced. And it is based upon this logic that occurs. Now, there's even more to this. So in 3 dimensions, now that you know the 3 pieces of logic, you have 2 hemispheres, you have pi times radius squared. Now, why is that? So if you have 2 dimensions, the tightest configuration that you can get is a circle, pi times radius squared. However, that is 1 dimension, 2 dimension. It's not a sphere because the other side is the 2 hemispheres. And so you always have those 2 hemispheres, and then you have this tightest configuration. Now, this one is laid over another because you already have little ones in here. It obviously, it's this size circle, but it's laid over ones that you've already built in the inner layers. That gives you the periodic table. So shell 1 is 2 hemispheres times 1 squared. 2 times 1 equals 2. Shell 2 and 3, remember the interlaced, is 2 times 2 squared. That's 4, equals 8 max. 2 times 3 squared. 2 times 9 is 18. And then the 4 squared for 6 and 7 is 16, making 32 max. That is the physical 3D logic of the periodic table. That logic explains chemical properties. It explains how shells build. It shows how they bond, what angles they bond at. Everything is based upon actual 3D logic that you can do by understanding this abstract world of quantum numbers, but as a hemispherical coordinate system. Now, it even gets funner. You see, the math is really strange. You see, here's the funny thing about that. If you're trying to do squares of units of measure, you're going to increase that x by 1 and square it. But the difference of that is 2x plus 1. So that means it's always odd. Let's do those ends again. Shell 1 is 2 times 1. But for shell 2 and 3, it is 1 plus 3, and 1 plus 3 is 4. Oh, that 4 is that same 2 squared. 1 plus 3 plus 5 is 9, and that is 3 squared. 1 plus 3 plus 5 plus 7 is 16, and once again, that is 4 squared. So the same thing that we had here for full shells now explains why we get 1, 3, 5, 7, or 1, 3, 5, building from pole to equator in the 3D hemispherical model that describes electron subshells. Now, please remember that this 3 is not there. There's really a ring of 3 and a ring of 5 and a ring of 7. And I just don't have the space to show the whole ring. But I do that separately when we do my dot diagrams to learn about bonding angles. Now, one final piece to try and understand this a little bit. You understand that as you're getting out here, these are pulled and all these ones line up. But as you're going out towards the equator, we have this interlacing. So you go 1, 3, 3, 5, 5, 7, 7. And so the distance here is slightly less. So as a result, this is slightly oblong. It's not really hemispherical, it's hemisoblongal, if that's a word. So when you do the 1, 3, and 5, these two are slightly inside. So as you're doing this, whenever you do a D, they always give you an n minus 2 count. It fills by this 3D logic, but the energy level is slightly inward, and the energy level is slightly inward. However, as you push those in, that actually pushes that one out a little bit, and thereby the P is actually slightly more than the S, and you might call that a scrunch, okay? Now, so these strengths are different, and that's what explains quantum numbers as electron subshells in a way that you can now visualize these things instead of it being abstract, even though there's still all this fun math underneath.